Alright, in this video we're going to be talking about how to handle collisions in hash tables using a strategy called probing. So one of the things that we're kind of able to take advantage of with hash tables is that they usually have like a bunch of elements that aren't being used. So the idea of linear probing is to kind of take advantage of that by anytime you face a situation where two keys are getting mapped to the same index location, you can basically just search for the next free location and store it there. So here's an example. So let's say we hash the UIN pictured here, and it hashes to the element at location 45,678. So we go ahead and place the element there, and then we hash another UIN, and it turns out it gives us the exact same location, 45,678. So what we're going to do is we're just going to search for the next free location and store it there. So all we do is we literally go to the next index in the array, and if that location is free, then we store the data there. Then if we needed to hash again and we got another collision, so here's another UIN that hashes to the index 45,678. Here we just walk. The next one is not free. We walk again. That one's free, and so we place it there. So when you are inserting, that's the process, and then when you are searching for something in your table, you can't just go directly to the location. You're also going to have to go and walk along the hash table to see if it's there in some of the other locations. So here is an example of what the code looks like for linear probing and what is different. So we have a struct, we call it a KV pair, key value pair, and we've added some additional member variables. So the first one is, the new one is that we have a Boolean that is called contains data that keeps track of whether or not there's data at that location. We also have created a constructor for our struct that's going to initialize that to false. So that way when we create an array of empty structs, all of those structs are labeled as contains data equals false. So here we're just creating a C array of KV pair structs. In this case, this isn't an array of pointers, this is just an array of structs, and so we just have a pointer to the front of an array of structs. Same as before, let's say we wanted to insert. So we need a key value pair to insert, and then we need a hash to get the index that's associated with that key. So in order to go ahead and find a free spot, we are going to call on that member variable contains data. So we're going to use the index to go to the location in the table, and then we're going to check its member variable. If contains data is true, then we basically need to walk to the next location and try again. If that one is true, try again, and you keep doing that until this is false. Once that's false, you're at an index location that's available, and you're just going to set the key and the value, and then also update the contains data member variable. So what happens if you get all the way to the end and you still haven't found a place to store it? Well, in that case, you're just going to wrap around and go back up to the top and start searching from there. So linear probing is best visualized as a ring because as you probe, you can go all the way around and back to the start. A lot of people like to think of linear probing as the probe actually being a ring where the first and the last element of the array are connected. In code, nothing fancy, you're just setting the index to 0 anytime you reach the last one. So that's all. That's all there is to probing. Obviously, the search has to be modified and all of that. Remove has to be modified, but the whole idea of it isn't that complicated. And in the Zybook's reading, they walk you through all the algorithms for chaining and linear probing. But from like the big picture standpoint, that's all there is to it. Another form of hashing that you might be interested to hear about is the Robinhood hashing, which is like linear probing with a slight modification. And I think it's just like a fun name. So with the Robinhood hashing, when you insert an element, if the element that you're inserting is further from home than the current element, then you'll actually displace that element to make room for the new one. And I just think it's a cute name. With like the idea of what Robinhood is supposed to be. But it's, just a slight variation. One thing to keep in mind with all of these collisions is that these algorithms don't work when there's a ton of collisions, right? So you need to be minimizing collisions for these algorithms to still be efficient. So that is probing.